the people gathered outside of me. Okay. Okay, you want to introduce them?
You see what is written here? So,
100% tested.
so this is from Juan Baldacena's talk.
Where's your shirt?
I'm a lazy guy.
Which group of Maryland are you?
Raman.
Raman. Oh, yeah.
He always speaks very highly of you.
Eh?
He always speaks very fondly of you.
We're very good friends. So. He's very nice. So
Same thing back to him.
So shouldn't you go to Phenomenology, Tassi? No.
Yeah, he's doing some more formal
So what? You're working on these things with him on black hole. So you're not doing any phenomenology.
He originally first put me on a phenomenology project, like anomaly deviations.
And
Then he started talking to me about holes and he got very interested in it since.
so he's looking at firewalls and all that.
Not as much, but first we were doing.
He wrote a paper a while back, right?
Yeah.
So it's continuing on that direction.
Similarly, a little bit. We were also doing an inflation project about this weak gravity conjecture.
Uh-huh. Is he still doing the scalar gravity cosmology? Or he gave up?
He still gives talks on it.
Yeah, but I've been waiting for his paper for 5 years now.
Every once in a while, this previous student critique would come over and they would work on it, but I'm not sure. So I think he only works on it when critique comes and visits. Pretty big.
So before we get started, I just wanted to say a couple words on behalf of all of the students, all of us, who really wanted to thank all the people whose hard work made CASI possible. And I know there's a lot of, definitely a combined effort that made this all come to fruition. So I know for me, and for everyone I've talked to, CASI has really been a wonderful experience. Both because of the knowledge we were able to gain through the lectures, but also just through, like the networking. CASI really has been a great venue for everyone. I think out of this there'll be definitely some future collaboration, but also just, some great friendships that have formed here. So because of all of this, like I said, I want to thank, we want to thank all of the people who work so hard. So first Sherry, of course. And Sarah. We got to thank Bobby back there for always doing it in the future. Veronica, who designed the webpage. Yeah, webpage was really helpful, especially when preparing to come here. So beyond that, definitely Tom. And then Joe and Pedro, who's not here, but we should also thank him. And finally, all the lecturers, not only the ones that are present. So thank you all a lot. I know, like I said, for me, this was really great.
So I guess I can start. Oops. Okay, so in this last lecture, in this last hour, I'll give you a lightning introduction to supersymmetric models for particle physics. So it's 1 hour. This is a field that has been going on for more than 30 years. And so I'll just give you an idea. And I will present some of the standard things in a slightly different way. And that, if you want, is the little amount of originality of this lecture. So other than that, it's not original at all. Okay? So, and I will assume you know the basics of supersymmetry, also because you were able to sit through 5 hours of lectures by Nati Seiberg, so you must know supersymmetry. Okay? So did he talk about supersymmetry breaking, right? Not so much. Because I saw in the documents he had posted there was supersymmetry breaking, but he didn't talk about supersymmetry breaking. Okay. Well, I had the wrong guess. In fact, I didn't. At the end, I didn't write to him. I didn't ask him because when I saw it, well, it's okay. It's okay. So, so this is the basic setup. So these are the fields that make up the minimal supersymmetric extension of the standard model. There's matter fields. There's a Higgs sector made of two chiral fields. These are all chiral. And then there are the gauge multiplets for color, SU2, and U1. And aside gauge interactions, a structure I will not review here, okay, the specific structure of supersymmetric gauge interactions. At the level of marginal or relevant operators, the superpotential is given by these terms, just the Yukawa couplings, plus a mass term for the Higgs. Note that there's no Higgs quartic or cubic term in the superpotential at this stage. But you could have a quartic, but it would be irrelevant. Superpotential has dimension 3. There are other terms that you could write. I discussed them yesterday. And these terms would be damaging. They will violate baryon and lepton number. And those terms can be forbidden, assuming that for some reason, at the more fundamental level, there exists a Z2 symmetry that distinguishes matter from the Higgs. And if you impose that symmetry, that is known as, well, that is equivalent to another discrete symmetry known as R parity, then this is all you have. And you see, it's very interesting already with respect to Technicolor, with this little Z2, what it buys us. It buys us so the problem of flavor that we saw right away in Technicolor, even without getting too excited, you really see the Yukawas and the things that you don't see, like this four-frame interaction, come at the same level. In supersymmetry, at the first stage, you don't have that, okay? You only have the Yukawa couplings, okay? You don't have junk, okay? You only have what you see. But of course, the model is not yet complete because it contains many more particles, okay? Many more particles that we don't see, all the partners, okay? So there is some extra step to be taken, and it is when you take that extra step that you start encountering the problems, okay? But we'll get to that in a moment. So let me, okay, so this is the structure. So let me now discuss in general the issue of naturalness in the case of supersymmetry. Naturalness meaning in the specific instance of natural separation of mass scales, okay? So now in supersymmetric field theory, in supersymmetric, again, we have the usual situation. We have two widely separated mass scales, and in the between, the theory is approximately conformal. So to decide whether the hierarchy is natural or not, we have to characterize the deformations of this fixed point. Now, in conformal field theory, in supersymmetric conformal field theory, the only relevant deformations can come from the superpotential. They are chiral. Because of unitarity, vector multiplets that can appear in the Keller potential, because of unitarity, vector multiplets have dimension equal or bigger than 2, and the Keller potential is an object of dimension 2. They are either marginal or irrelevant. So you cannot get any, so you don't have relevant, so the operators in the Keller potential, they cannot push away from the fixed point, and so they're not important in the perturbation of the hierarchy. What really matters for the generation of the hierarchy are the superpotential or the gauge interactions. Okay, in the superpotential you can have relevant operators. Okay, this is an operator of dimension 2. Superpotential has dimension 3, so this is relevant, and these ones are marginal. And you could even have lower dimension objects. According to unitarity, the lowest dimensionality of a chiral field is 1. Okay, so you have ample space for relevant deformation. However, there is a remarkable feature. So in order to study hierarchies, you have to focus on the superpotential. However, the superpotential is a very remarkable object. It is a chiral quantity. Okay, it is, if you want to call it holomorphic, it's just a function of the chiral fields. And because of this property, because of this property, the whole discussion about the renormalization of the superpotential, or if you want, of how the superpotential can be affected by short distance physics. Remember, the whole discussion was, okay, I have an effective Lagrangian, I have some parameters that describe the effective Lagrangian. How are these parameters affected by physics at shorter distances? Now, the superpotential is very, very little affected by that. Okay. In fact, you can prove there's a well-known theorem known as the non-renormalization theorem that establishes that the superpotential is not at all renormalized in perturbation theory. And the reason, the way you can prove this non-renormalization theorem, which I believe Cyber discussed, or he did discuss, it's a beautiful instance of use of selection rules. Selection rules for all the, you can assign transformation property to all the coefficients here. These coefficients coupling can be viewed as chiral superfield themselves, and using the holomorphic of the superpotential, you find out that the way these quantities, this coupling can appear in quantum fluctuations is very, very limited, and in particular, they cannot renormalize the superpotential, okay? At least in perturbation theory. Beyond perturbation theory, the superpotential can be renormalized, but even there, what you can get is quite often very, very constrained and non-generic. Okay, so in view of these things, the notion of naturalness, as stated by R parameters consistent with selection rules, in supersymmetry takes a new flavor. Okay, besides the ordinary selection rules, there is this feature of holomorphy that really matters, okay, and that constrains how parameters affect one another, okay, and that's the basic reason why supersymmetry is relevant for the hierarchy problem. Okay, that's the basic. I mean, you have this feature. So, for instance, just to give you an example, consider a superpotential for two scalar fields. Okay, one you give a mass m1, another you give a mass m2, and then you add all possible interactions. Okay. Write all you can, all possible interaction involving these two fields in such a way that there's no symmetry, and these interactions are sizable. Okay, they're not small. Okay, in such a way that there is no symmetry preserved by these, no global symmetry preserved by these interactions. Okay, no phase rotations of phi 1 or phi 2 is preserved. They are all broken. Okay, so in that circumstance, in the limit where this mass goes to 0, you don't recover any new symmetry. Okay, it's not, strictly speaking, from the point of view of symmetries, of global symmetries, this point is not a special point. It's not a point of enhanced symmetry. And yet, there's no way to give rise to this mass, even if this mass here is non-zero, in the presence of the most general interactions here. In other words, this term is not normalized no matter what the symmetry properties of everything else is. Of course, there is and this is just a consequence of holomorphy. Okay, so holomorphy increases the power of selection rules. Okay, it even pushes them beyond where you think they work. Okay, it's interesting to notice that in this case, in a situation like this, there's really a well-defined, in a situation where M1 is much less than M2, there's a well-defined notion at all energy scales of M1 being much less than M2. Okay, if you compute the correlator of phi 1 with itself, the mass insertion in this two-point correlation will be small at all scales. You can identify what it is. You can identify it by just looking at the correlator of the fermion inside phi 1. And you will see that this two-point function, this chiral breaking part, is small. Conversely, if you have a non-supersymmetric theory, so n equals 0, And you have a similar situation. Rather than the potential, you have the superpotential. You have m1 square, phi 1 square, plus m2 square, phi 2 square, and plus you add all possible interactions that mix the two fields, okay, in such a way they talk to each other, and there's, well, okay, already these are scalars. There's no way in which there's an approximate shift symmetry of phi 1 that can protect it. There's nothing like that. They interact in a very important way. Well, in that situation, if you want the mass on phi 1 to be the physical mass of phi 1 or to be much smaller than the mass of the other, you really need to cleverly tune your parameters. And you can see that in the following way. Unlike in this case, the notion of m1 being small is not a notion that is well defined at all RG scales. Okay, if you look in this model here, just to give you an idea, if you look at the RG evolution of the mass, imagine you are in a situation where m2, so there is, let's say here there is the physical cutoff, lambda. So this is the RG scale, okay? This is lambda. Imagine this one is m2, okay? And so already there is an issue, okay? If there are important interactions, there is an issue why m2, even m2, is much less than lambda. But let's assume we have swallowed this grudging pill, okay? We have tuned m2 to be much less than lambda. And now the question is, we want more, we want even m1, the other one, to be much less than m2, okay? Now, if you look at their G evolution between m2 and lambda, these two parameters mix like hell. If the coupling is important, they go into one another, they talk to each other, okay? And particularly, if you look at the value of m1, okay, square as a function of their G flow, you see that even if it starts small, it will go up because of effects due to m2. It will go down here, and then at this scale here, m2 is integrated out. The RG evolution is frozen. From this scale down, m1 is normalized multiplicatively, and it will basically change by liter. Okay? But if you want m1 to be small, okay, and it will be of order m2, so it will not be small in any way. If you want m1 to be small, this guy should run, and then when you freeze the RG evolution, when m2 is integrated out, it should precisely be the point where it crosses 0. Okay, so in other words, so m1 evolves, it gets contribution from m2. Generically, it is of order m2 on any point on the RG trajectory. But what you want to have a physical mass m1 equals 0, the running mass should cross basically 0 at the point where you integrate out m2. Okay, I don't know whether this concept is clear, but that is related to the fact that m1 and m2, so that there's no way to really characterize m1 being small at all scales. Okay, while in this case there is. Okay, m1 in this situation here is not renormalized. Well, in fact, it is renormalized, the running m1, only by wave function normalization, but that's an added, it's a multiplicative renormalization. So, if the second part of the discussion was confusing, just stick to this, okay? Just stick to this and just think of what you have learned in the course of supersymmetry, that the superpotential is not normalized. So if I start with a very, very tiny mass at one point, that will stay like that. It will stay the same. Now, non-perturbative effects can change this state of things, okay? But in weakly coupled theories, the theories that start weakly coupled at the UV scale, certainly we can be confident that the non-perturbative effect having to do with infrared dynamics will not dramatically change things. At the very worst, if you want, you will get contributions that are like the cutoff scale times e to the minus 1 over g squared. So they're exponentially small. Okay. So that's the main reason for interest in supersymmetric theories as regards the hierarchy problem. Now, in particular cases, however, it can happen that a certain mass in the superpotential being set to 0 coincides with the presence of enhanced symmetries. And that is the case of the MSSM. Okay, in the supersymmetric standard model, in the limit where mu is set to 0, the system gains an extra symmetry, called U1 Peccei Queen. You can define the symmetry to be the symmetry under which H2 rotates by a phase. The up-type quark rotates by the opposite phase, all of them. The up-type quark multiplet rotates by the opposite phase. And everything else is untouched, okay? According to this symmetry here, okay, this object here is invariant. This object here is trivial invariant because no field transform. This is invariant. And this guy is not invariant. And mu transforms. You can formally reestablish the symmetry by stating that mu transforms like e to the minus I alpha mu. Okay? So mu is a parameter transforming under the symmetry, and the point mu equals 0 is a point of enhanced symmetry. So it's a special point. So you can characterize the point where the Higgs mass vanishes as a special point of enhanced symmetry. Something that you cannot do in this case here. The case, again, or in the standard model, from the perspective of take the standard model as an effective theory, from the perspective of the UV theory, okay, from the perspective of the symmetries that are valid at the ultraviolet scale where you define the theory, M Higgs equals 0, the M Higgs of order, the cutoff square, have absolutely no distinction. Of course, they have a very big distinction as regards infrared physics, okay? But as regards the selection rules that are operative at the ultraviolet scale, they have no distinction. In the case of the supersymmetric standard model, instead, the case where the Higgs mass is 0 is special already from the perspective of the theory at the cutoff scale. I cheat a little bit here because this symmetry here is not really a symmetry. Can anyone tell me where I cheated? Already the name. Peccei Queen. It's anomalous, right? It's an anomalous symmetry. It has a QCD anomaly. So should this mean that at the level of the more fundamental theory, whatever string theory there is at the fundamental scale, tells us that we are full of it, in the sense that we used it, but we cannot use it? Well, I don't know. Okay, I can tell you that the practice is, okay, the practitioners, is to assume that the effects will not be smaller, will not be bigger than the non-perturbative effect that you would expect in the low energy theory, this is to say in the standard model. And those effects are small because the theory is weakly coupled. They're just exponentially suppressed. Okay, so we go by the belief, which could be not well founded, that this symmetry is that any breaking that may come from ultraviolet physics is not worse than is not more important than the non-perturbative breaking associated to the QCD anomaly. But this could be. And anyway, even at the level of the more fundamental theory, we can always invoke a non-renormalization theorem that is always valid also at the level of string effective actions. Okay, even in those cases, being able over normalizing the superpotential is very, very, very difficult. Okay, so the normalization of the superpotential, even at the more fundamental level than the field theory I'm considering here and that I can manage, is a very, I mean, the normalization of the superpotential is subjected to very strong constraint, and and again, it happens non-perturbably. For instance, in certain classes of string models, you can start at the you compactify, say this is like heterotic compactification, I think, where you start at the lowest classical order, superpotential is 0, and the Yukawas get then generated, and you have these guys associated with different fixed points in an orbifold, and these Yukawas are generated by worldsheet instantons, and they are suppressed by an exponential of the area times the string scale square, and the times ms squared. So if the volume compactification is sufficiently large, then you get exponential suppression. Okay, and similarly for mu, one could expect. Okay, so this is just to tell you the specialty. Okay, and now often you hear, based on this Pacheco symmetry, one way in which normally this special property of the massless Higgs is stated in supersymmetry is the following: is that the Higgs mass that you get from deriving the potential from this term here for H1 and H2 is equal to mu star mu, okay? Where mu is the mass of a fermion, okay? Is the mass of the Higgsino. So basically, in the supersymmetric standard model, the mass of a boson of the Higgs is just the square of the mass of a fermion, of its fermionic partner, the Higgsino. And we know that the fermion masses are protected by chiral symmetry. And thanks to supersymmetry, the Higgs and the how do I draw it normally? Okay, the Higgs and the Higgsino are related. And the Higgsino, and by supersymmetry, they must have the same mass. And if the Higgsino is protected by chiral symmetry, so is the Higgs. So that's one way. That's one of the vulgata of why supersymmetry is important. Why supersymmetry is relevant to the hierarchy problem. Okay, and again, this is also interesting. The fact that this is Pacheco symmetry is also interesting in case you want to try to explain the origin of this new parameter, okay, why it should be small, okay, because it's clear that if you want to solve the hierarchy problem, this new parameter should be of the order of the weak scale rather than the Planck scale, okay. The fact that there is a symmetry that protects it, no matter whether it's anomalous, will give us a handle to perhaps, it sets the stage for a dynamical explanation of why mu is small, okay. That's the usual thing. When you have very much like for the neutrino mass in the Fermi theory, there we had the lepton number, okay, explaining it, and then in the standard model we understand that phenomenon as that lepton number arises in accidental symmetry. Well, the main thing happens here, okay, so it's an important part of the picture. Now let's discuss let's try to discuss the phenomenology of this model without just the model the way it is, okay? So then the model with the way it is not phenomenologically viable, okay? It doesn't do what we see in experiment, okay? First of all, when mu is different than 0, the vacuum is at H1 equal H2 equals 0. Okay, there's no electroweak symmetry breaking. Okay, in fact, there are some flat directions where you also break, however, lepton numbers. But let me not talk about those. Okay, that would even be worse. If you don't break if you don't do anything even more dramatic, you cannot break electroweak vacuum. And if mu is equal to 0, okay, there is a manifold of vacua that break electroweak symmetry. This is along the D flat directions where H1 has an expectation value like this. Like this. 0 and H2 has an expectation value like that, exactly equal. Okay, such a way that the D term proportion to H1 square minus H2 square in this case is equal to 0. Okay, so that this is a flat direction. Okay, so when mu equals 0, basically this V is a modulus, and you have that V can go from 0 to whatever you want and Planck. Okay, that is also so here electroweak symmetry is broken. Okay, however, there is some major problem. What is the mass of the Higgs in this situation? Actually, it's a flat direction. It's 0, right? It's 0, so it doesn't work. Okay, so we know for sure it doesn't work. And not only that, the MH is 0. and the mass, for instance, of the electron and this electron is the same because supersymmetry is unbroken. Okay, so supersymmetry. I mean, in this situation here, on this manifold of vacuum, which is the only one you have, supersymmetry is unbroken. So you have MH equals 0 and you have no splitting within the matter multiplet, so you have all things that you don't see, scalar electrons and all that. Okay, so now, which this means that in order to get a realistic model, we have to do something else. What we have to do is to break supersymmetry. Now, how do we break supersymmetry? Well, supersymmetry must be eventually a gauge symmetry, okay? Because we want to include gravity, and the graviton will have a partner, and the partner will be a particle of spin either 3½ or 5½. Let's say it's 3½ is the gravitino, and this is a higher spin particle. In order to make sense of this higher spin object, to have the right number of velocities, you need an additional gauge symmetry. Okay, that is a fermionic gauge symmetry, the one that shifts the gravitino field. So in other words, supersymmetry must be made local. That's a very, very practitioner way of saying that supersymmetry must be local. So supersymmetry, the breaking of supersymmetry, therefore supersymmetry must be upgraded to a local symmetry, which means that there's no such notion as explicit breaking. Okay, a gauge symmetry is never broken. Okay, can be different phases depending on whether you have the corresponding Goldstone bosons or Goldstone fermions that pair up with the gauge field to give it a mass. But the breaking is always, in a sense, spontaneous. There's going to be some field that acquires expectation values and so a field that provides the suitable Goldstone bosons. Okay. I'm just saying that because at the beginning, even though supergravity already existed, the attitude was to break it explicitly by adding the so-called soft terms. But you see from the beginning that the breaking is going to be described as a spontaneous breaking. Okay, so how to proceed? What classes of spontaneous breaking can we consider, and how do we get in a little step in the right direction? So the first thing we can think of, first of all, spontaneous supersymmetry breaking. There are various ways of breaking supersymmetry spontaneously. I thought here I could skip, but now I realize that I cannot skip completely. Let me say just a few words. Supersymmetry can be broken spontaneously by having a suitable, for instance, superpotential for a bunch of chiral fields. Models of this type are known as O'Rafferty models. Okay, and the breaking of supersymmetry in this model is reflecting the fact that these systems don't have a ground state of zero energy. Okay, and given that Q supersymmetry generator commuted with Q dagger, anti-commuted with Q dagger gives you the Hamiltonian. Okay, if the energy density of the Hamiltonian is non-zero, supersymmetry is broken spontaneously. Okay, just from the algebra. And the way this breaking is and there's going to be a Goldstone fermion. Okay, there's going to be a Goldstone fermion, the Goldstino. But let's forget for a moment what problem may it give. In fact, we will forget throughout this discussion. In fact, let me say, the Goldstone fermion will get a mass because it will be eaten by the gravitino. So that's it. Okay. So the way this breaking manifests itself in practice, okay, will be that there's gonna will be the way it will manifest itself is that there will be some chiral superfields. Okay, the chiral superfields have when you have a chiral superfield, there's a scalar component, there is a fermion component, and there is what is known as the auxiliary field. I hope there is some familiarity here. If there is no familiarity, then 1 hour there's no hope. I mean, the breaking of supersymmetry is encapsulated in the fact that there is the highest term in the multiplet, the highest element of the multiplet, the F term or the auxiliary field, acquires an expectation value. Okay. In a sense, the breaking of supersymmetry is, from the point of view of superspace, is very similar to the breaking of, say, translation invariance as it happens in a fluid or in a solid. Okay, there is a field with expectation values, with an expectation value that depends on the space-time coordinates. Okay, that's precisely. So you can think of a supersymmetry breaking as a fluid in superspace. Okay, and the Golstino is like the sound wave, with the corresponding object. I'm stretching it, but the way it is. So. So the question is, the zeroth order question is, can I now modify the supersymmetric standard model by adding extra stuff in such a way that I had new fields? If you want, I extend the Higgs sector, I add additional chiral multiplets coupled to the Higgs, H1 and H2, in such a way that these other fields, one way or another, break supersymmetry spontaneously. And by talking to the Higgs, also the Higgs will have the same property. This auxiliary field for H1 and H2 will have non-trivial expectation values. And then the Higgs communicating with the standard model fermions, multiplets will communicate the fact that supersymmetry is broken to the matter multiplets and hopefully change the state of things. Okay? Now, it's very easy to see that this is not possible if this is done simply by adding new interactions in the chiral, in the superpotential. Okay, that is by adding, if you want, renormalizable interactions, interactions that are relevant at low scale. Okay, you cannot do that for a very simple reason. Okay, if you remember so at the supersymmetric level. If I look at I have two selectrons. I have two partners of the electron. One is, let's focus on the electron for instance. The electron, there is a right and a left electron, and so there is a left and a right selectron. Okay, and in the limit of unbroken supersymmetry, the mass matrix of the selectrons, left and right, is given by E selectron left dagger star, E selectron right star, M electron square, and here is 0. E electron, selectron, E selectron right. Okay, it's just coming from the superpotential. Now, unfortunately, I really chose the two most far away blackboards to have this discussion that I keep go peripatetically on and forth. Now, if somehow H1 is coupled to a supersymmetry breaking sector and it acquires an F term, let's say H1, as an expectation value that is just breaks electric symmetry, plus an expectation value, let me call it F of, there is V1 plus F1 theta square. Okay, it has some expectation value. Okay, and so by that expectation value, it will modify the mass of the corresponding scalars. Now, it's a little computation in beginning supersymmetry to see what the implication of this effect of this term vacuum expectation value is here. It induces a mass term of diagonal that mixes the left and the right selection. It induces a mass term here, proportion to lambda electron times F, lambda electron times F. Okay, so the math matrix has this form. Okay, and now you see what happens. Okay, it only affects the off-diagonal term. So before you had the selectron left and the selectron right, they were degenerate in the limit of unbroken supersymmetry. But now you only add off-diagonal term, and what you will have, and they will have the same mass as the electron. But now, if you only affect the mass matrix of the selections by adding off diagonal terms, the trace will stay the same, which means that the two levels will go one up and one down. Okay, they will repel in this way. Okay, there will be some multiplet. There will be some eigenstate E1 and eigenstate E2, but E2 is always lighter than the electron. No good. Okay, we don't see any such thing. Okay, so the discussion can be slightly refined by taking into account also D terms, which I did not do, but the thing doesn't change. The essence of the argument is that you have an off-diagonal effect, and therefore you don't split the masses. Very good. In order to split the masses, you need a supersymmetry breaking effect that comes from the Keller potential. That's the only way. Okay, the Keller potential. There are kinetic terms. Okay, d for theta. There's gonna be L E dagger, L E, plus E dagger E. These are and because of gauge invariance, you cannot have these mixing that, so that they are diagonal. And now if there is some agent, some field, okay, some field, which acquires expectation values in its theta-dependent terms, then you will be able to add diagonal terms here. Okay. However, this interaction here, given that this object has dimension 2, is always irrelevant. Is always an operator of higher dimension. Okay. So let me recap the logic. The superpotential introduces effects in the masses. Okay. But these effects are of diagonal, so it pushes one up and the other down. And we would like to push them all up because we haven't seen anything. Okay. However, the superpotential was our only chance to get an effect via the normalizable interactions, to say interactions of dimension less or equal than 3. Therefore, so the superpotential doesn't work. We have to go to the only other object we have in the supersymmetric Lagrange, that's the Keller potential. But given that the low dimensionality, I mean the Keller potential has to have dimension, it has dimension 2. Whatever you do puts you in the domain of non-renormalizable terms. That is to tell you that the breakdown supersymmetry necessarily must be communicated to the supersymmetric standard model via non-renormalizable interaction. Okay, and therefore this is the picture. Let me just give you the overall picture. Okay, let me give you the overall picture. By the way, I started a few minutes later, right? I have 5 to 10 minutes more. Okay, thank you. Eliminate this. So given that supersymmetry, whatever supersymmetry breaking dynamics exists, must be coupled to us via non-renormalizable interactions, the sector that breaks supersymmetry is often called the hidden sector. Okay? And now, how hidden depends on the model. Okay? But in general, it's hidden just means coupled via irrelevant interactions. Now, the question is, how can irrelevant interaction give any important effects? Well, you will have ratio of mass scales, okay? And ratios of mass scales, okay? Dimensionful ratios of mass scale can give to whatever you want, okay? I'll show you in a moment. So let me give you the basic picture, okay? Basic picture of supersymmetry breaking. the basic picture is the following. There exists some ultraviolet physics at scale, let me call it M. Okay, M could be the Planck scale, okay, could be the GATT scale, could be 100 TeV. Okay, it's some scale much bigger than the Wick scale. And you, at that scale M, two sectors emerge. Okay, and these two sectors are only coupled to one another via irrelevant interactions. How that could happen? It could happen just as a result of, if you want, gauge invariance or properties of the two theories. It could be that gauge groups in the two sectors are such that there's no way to write an operator that couples them of dimension less or equal than 4 in the Lagrangian. Okay, so the two sectors are coupled only the interactions suppressed by power of 1 over m. And one of the two sectors, okay, is let me try to be. One of the two sectors is the sector that breaks supersymmetry. Okay, and it is characterized by a scale ms. Okay, this sector could be some theory, okay, some supersymmetric gauge theory that at the scale ms does precisely what QCD does to chiral symmetry at scale lambda QCD. It's a gauge theory that at the scale ms confines, okay, and breaks chiral symmetry, and among other symmetry breaks, it breaks supersymmetry. Okay, all that at the same scale. Okay, an example, a very simple example of this, okay, is the following theory. It's SU5 with a 10 and a 5 bar. Okay, just take supersymmetric SU5 with a 10 and a 5 bar. It's another group. This is a strongly coupled gauge theory. It's characterized by just one parameter, the strong scale of the gauge group. And this theory is proven. You can prove that this theory at the scale also breaks supersymmetry. Okay, it's a beautiful example because this theory has no other marginal deformations than the gauge coupling. Okay, you cannot write any superpotential with just a 10 that is antisymmetric and a 5 that is the fundamental. You cannot write any invariant. Okay, and then the other sector is the supersymmetric standard model. Okay. Supersymmetric standard model. Okay. And these two theories in the between there are approximately CFTs. Well, this is free, and this is a CFT perhaps interacting. Okay, approximate CFT perhaps interacting. Now, the statement that this theory breaks supersymmetry can be made technically the following way, in the following way. Below the scale ms, okay, so let's think in concrete terms. At the scale ms, the theory will create a gap, and virtually everything in that sector can become massive, apart from one particle, okay, the Goldstino, okay, the Goldstone fermion of spontaneously broken supersymmetry, okay. So, to the very least, below the scale here, so in this range here, okay, you have just a Goldstino EFT. Very much like in QCD, below the QCD scale, you have a pion EFT. In this theory, below the scale, you have a Goldstino EFT. I mean, the only degree of freedom that really necessarily you must have is the Goldstino. It's possible that there may be other light degrees of freedom, but those are not necessary, okay? They could be seen as additional complications. And the Goldstino superfield, that's a very nice way how you describe Goldstino superfield. It's very similar to when you have a scalar field phi I, okay? And phi I in some SON, transforming as the fundamental of SON. Okay, and now you concoct your potential in such a way that on the vacuum, phi I is different than 0. Okay, and now your system will be described by n-1 massless degrees of freedom, the Goldstone bosons. Okay, and the nth and 1 massive, the radial mode. And this radial mode can be parameterized. A good interpolating field for the radial mode is phi I. It's just the norm of this phi. From the point of view of a low energy effective Lagrangian, you can treat this radial mode as frozen because it's massive. So effectively, you can parameterize the low energy effective Lagrangian by what is known as a sigma model. That is to say, a Lagrangian with a field phi I subject to the constraint phi I square equal to v square. Okay, so a Lagrangian with an SN symmetry subject to this constraint describes the most general Lagrangian for the n-1 Goldstone bosons. In the case of supersymmetry, and this was, this goes. The thing I'm going to describe now was worked out long ago by the people working in supersymmetry, but there is a very nice paper in recent years by Komargovsky and Seiberg that, in my opinion, they wrote it in a way that is modern and you can understand right away. And the analogy of this is that you will have a chiral field phi. Okay, the Goldstino effective theory is described by chiral field. So let me call it phi. Let me call it X. Chiral field is the Goldstino superfield. I think I have to speed up. And it is in the linear effective theory, when you have integrated out everything else, it satisfies the constraint x squared equals 0. Okay, it's a nilpotent chiral field. Okay, and you can solve this constraint. When you solve this constraint, you will find that chi is equal to. Now let's hope I write it correctly. Chi. This is the Goldstino bilinear over f. F is an auxiliary field plus chi theta plus f theta square. I think you have to put some square roots of 2. 1, 2. There's the square root of 2 here. Okay, there's a square root of 2 here and the 2 here. And you can check that if you square this object, it's 0. And the only two dynamical variables here are chi and f. Well, f actually is an auxiliary field. You integrate it out. And the most general Lagrangian for this object is the following. It is d for theta. It has a Keller potential that is an arbitrary function of x and x dagger. Okay. Plus a superpotential that is the only thing you can write down subject to this constraint here. Okay, a linear term. d2 theta ms squared x plus admission conjugate. That's it. So the basic statement is that the assumption that supersymmetry is broken just boils down to the assumption that below the scale, the hidden sector is described by this Lagrangian, where there is a chiral field x with a Lagrangian like that. And when you solve the equations of motion for f, this Lagrangian implies that f, the expectation value of f, is equal to ms squared. So supersymmetry is broken. Okay? So here, let me write it. So you have the Goldstino superfield, x satisfying x squared equals 0, and with the expectation value equal ms square theta square. Okay? Of course, this guy here also contains a dynamical Goldstino. We will forget it, okay? And that's for another lecture, okay? It's not relevant for what we're going to say, okay? Very good. So now these effects of breaking via this irrelevant interaction will hit back the standard model, and they will allow us to write masses for all the things that we have not seen in experiments, but which we hope to see soon. Okay, perhaps we'll never see. But then, if we don't never see, then my explanation is even better. It explains why we don't see them. Okay, and in line with the philosophy, the theory here will be an approximately conformal field theory. So the interaction between these two, between this sector and this sector, will be dominated by the lowest dimensional operators. Okay, and here we are in n equal 1. Okay, the lowest dimensional operators, I will take them to be a chiral field S, chiral superfield S, with dimensionality delta S. Okay, and a real vector field R with dimensionality delta R. Okay, this is a multiplet that contains at its lowest component a scalar field. Okay, of dimension delta R. It contains a current of dimension. What is the dimension of the current inside this guy here? Delta R plus 1, right? This contains a current with dimension delta R plus 1, and so on. Okay? So you know that the currents must have dimensionality bigger or equal than 3. So the dimension of delta R is bigger or equal than 2, and the dimension of delta S is bigger or equal than 1 from unitarity. Okay? In particular, there is the case that is most popular among phenomenologists, is where there is S, where is the one where this theory here is approximately free, so that S is just some chiral field, okay, with dimension delta S 1, and R is equal to S dagger S, and it has dimension 2. Okay, this is the free most popular case. But you can, and this is the case that was mostly considered for the first 20 years of supersymmetry. Starting 15 years ago, when we started learning, we practitioners of supersymmetry, we started learning conformal field theory, we started doing more exotic things. Okay. Okay. So now, so these guys, so this is an example. Okay. So these guys are going to be coupled to the fields in standard model. You can now write, okay, the most general Lagrange that couples the two sectors. Okay, the idea is to write all the possible operators that mix this with that, suppressed by powers, inverse powers of 1 over m. And in the course of this discussion, I will indicate with phi, okay, is any field of the standard model, any chiral field in the standard model. It's U, L, Q, the Higgs, everything, okay? So let's see what we can have. So we can have the following object. You can have d for theta phi, and I'm suppressing all possible indices. Here you can have indices, different flavors. Let me suppress just to give you an idea. Okay, phi dagger phi. This can couple to R, suppressed by m to the delta R. Okay. It can also couple to S plus S dagger, suppressed to m to the delta S. Okay, this is one thing. You can also have interactions in the superpotential. First of all, you can have interactions that involve the gauge fields, delta S W alpha square, and this is any field strength supermultiplet of the standard model, color SU2 or U1. You can have objects that involve, let me not write the indices, S m to the delta S. Let me now really say what I want here is like Higgs. How do I write it here? It's Higgs phi phi. In fact, let me just say that the Higgs is just another thing. The Higgs is the Higgs. H is H1, H2. Okay? So this is any interaction like the Yukawa coupling. However, now this is a new interaction. In general, here there will be indices that have nothing to do with the Yukawa couplings. Okay? Here you see how we start having new structures that were not there in the beginning. So all the terms here and here can have indices, okay, coupling that I did not indicate, that introduce new sources of flavor violation. And there's going to be specific terms for the Higgs sector that I will probably not discuss because time is running short. But you can have, there are specific other effects. For instance, in the, well, let me say it. You can have terms like this. You can have terms specific of the Higgs sector, like d for theta, h1, h2, s dagger over m delta s. You can have terms like this, or you can have terms plus h1, h2, r, m delta r. Note that this term here is non-holomorphic overall, but from the point of view of the standard model part, it is holomorphic. It only involves two chiral fields. And this term will be relevant for the origin of the mu of the Higgs mass. And I probably will not have time to discuss that. Okay. So now you can discuss very quickly what the consequences are. Okay. Let me again number these terms. Okay, as I did before cases. Let me call this guy here 1. This is 2. This is 3, and this is 4. Okay, and now. Oh, there's one thing I should say. Sorry, there's one thing I should say before I do all this. The thing I should say is the following. Now, in order to work out the consequences, so this is the Lagrangian. This is the Lagrangian that mixes the two sectors in this regime. Okay, in the regime of between m, the cutoff, and the scalar supersymmetry breaking. At the scalar supersymmetry breaking, you change the description. These R and S will now have to be matched to the low energy theory. That is the theory of the Golstino. Okay, and just on general ground, you expect that at the scale at m at scale ms match to Golstino theory EFT. And how do you do this match? You just match the operator between the two regimes. Okay. So what do you match R to? What do you match R to, in your opinion? It's a general vector superfield, real vector superfield. What do you think you'd match it to? See, he's a phenomenologist. We spot him right away. He's the odd guy here. X dagger X, only X dagger X? Well, in my normalization, I'm an old-fashioned guy. I've taken X to have dimension 1. So you have to fudge in some m to the s. It's the only scale you have at hand when you do the matching. Delta R minus 2. Okay? Is it the only thing? No, you could also have X plus X dagger m to the s delta R minus 1. Okay, you could also have that. Okay, this is any real superfield. You can add a chiral plus anti-chiral. Okay, it's still a real superfield. Let's forget about this for a moment. It's not going to affect the discussion. I mean, it's not adding more information. And S modulo no symmetry forbids it. Okay, modulo no chiral symmetry. This is a chiral object, so there could be some overall chiral symmetry that tells us that S doesn't match to anything. Okay, but this matches to, in general, to X ms to the delta S minus 1. Okay, so now and now we know that this field X has an expectation value in its auxiliary component. Okay, it depends on space-time. So the expectation value of X breaks supersymmetry, or space-time symmetry, and via these operators, via this matching, the breaking will be communicated to the standard model field. Okay, and what do we get? Okay, what do we get? Okay, so now I insist we have this Lagrangian, we have that matching. We can now, we can just work out either by computation or just well, okay, by computation, but here I'm not doing any computation. Okay, so, or in practice, what we will have, sorry, I should say it better. Oh no, up and down. Now I'm becoming panicky because time is running short. Now it's going to be a show, okay, because it's going to be a comical show. So this will just boil down to, let's forget this, is like ms to the delta r, okay, plus 2, theta square, theta bar square. See, when I use the expectation value of x here, this will become that. Okay, r will become that, and s will become this. ms to the delta s plus 1, theta square, theta bar square. Okay, and now just by making this substitution in this Lagrangian here, we will be able to read what terms, what supersymmetry breaking terms are generated in the observable sector. Okay, and we get the following classes of effects. Okay, first, the operator 1 will give us particle masses, fermion masses, plus Higgs. Also, the Higgs will get something like that, masses. And the masses, these masses, go like, let me write like this, go like ms to the delta r plus 2 over m to the delta r. Okay? And if the sign is suitably chosen, these masses are positive. Okay? And you see here there's a ratio of scales. This, all we want is that these masses are bigger or of the order of their experimental bound, that is of order of 100 GeVs. And now you see here that we can choose the ratio of a mass and m even to be, they could virtually be very, very large. Take, for instance, the case delta r equal 2. You could take m to be as big as m Planck, and a mass equal 10 to the 11 GeV. You get the ratio here, you get 100 GeV roughly. Okay, so that's an example. So the physics that gives rise to this could be way, way, way out of reach. Okay, so this sector is really a hidden sector. Okay, then we have number 2. Now, number 2 is an interesting exercise to see what happens in number 2, because number 2 is what in conformal perturbation theory, whatever, is known as a redundant operator. Okay, number 2 can be, by filter definition, phi goes to phi 1 plus s over m to the delta s. Okay, can be eliminated in linear order. Okay, this filter definition via the Yukawa couplings here, when I shift the field, okay, will generate terms in class 4. Okay. However, we will be left with the term. This kills the thing in linear order, but we will be left with a term left with phi dagger phi, s dagger s, m to the 2 delta s. Okay. But this is not an operator we like from the point of view of the conformal theory. The operators are s and r, so we should still use an OPE, a computation, to translate this into RR dagger. So basically what we have to do is the OPE s with s dagger, which will contain r, to turn it into an r. Turns out that if you do the computation carefully, now in this computation there will be a mass scale to fudge in, because delta s and delta r is not twice delta s. And the question is whether the scale you have to fudge in is an IR or a UV scale. Now, it turns out it's a UV scale. Okay? And there's been some confusion in the literature, some debate between people. And there's, for instance, a paper by Shi, Craig, and Knappen, where they come through 4 different ways of doing it. The simplest way to understand it is just because this term is proportional to the equations of motion, okay? And when you insert it, the equations of motion always give you point-like effects, okay? And therefore, that tells you, when you will do the computation, that the scale you have to fudge in is the UV scale. You can do an explicit computation. So this term here will be nothing but the term we have already considered, r m to the delta r. So this is not adding anything new, okay? Then you have the 3. 3 is adding the gaugino masses. the mass of the partner of the vector bosons, okay, m1/2, that will go like ms to the delta s plus 1 over m to the delta s. And this other term here will generate the so-called A term, which I can forget in my discussion. Okay. So now you see that this is the basic two things you have to focus on. Okay. Okay. What should I say here? So you see, depending on the dimensions of delta r and delta s, you can have a situation where the corresponding masses for the gauge fermions or for the matter scalars are one bigger than the other. Okay. In the ordinary case, so let me now discuss the please.
With the Gigeons, is also an issue of R symmetry.
Sure, I assume that everything is. Yeah, I did not assume. I could have said an R symmetry. You could have invoked an R symmetry, for instance, saying that this is not there, or that this does not match. If an R symmetry is not broken in this theory, or some global symmetry, yeah, you can always have. Yeah, I'm disregarding. I'm just assuming that the most generic thing happens. In fact, this I think is the most interesting thing. By the way, if you have an R symmetry, then you're not well off, because you don't generate the gaugino masses, and then the gauginos have to be somehow, or they're suppressed, and they should be observed very early on. And the gauginos are not those that are the most important for the Higgs. The one is the stop. So that if the gauginos, whenever the gauginos are lighter than the stop, you're not starting well.
So this framework includes what's called gauge mediation. Right?
Gauge mediation is included in everything. This includes everything. Okay, this includes everything. In gauge mediation, the scale m is the mass of new fields with standard model quantum numbers. Okay, and these fields have standard model quantum. They are massive. The standard model quantum numbers, and they are coupled via gauge interactions to both sides. No, these guys are coupled to standard model with gauge interaction, and they're coupled to these guys to whatever they want. Okay, and then they mediate. Yes. Or in gravity mediation, okay, if you want, these are just whatever Planck's law you have. You don't know what string scale modes, okay. And now, so let me tell you briefly about the various possibilities, but I think I should go fast. There are basically three options you can envisage. Okay, so notice that this will tell you the overall mass scale of the gauginos, the partners of the fermions, and of the ordinary matter, the stop, the Higgs, everything like that. Just have to check whether I've forgotten something in the discussion. Okay. Okay, so basically what you have from this Lagrangian is that you have in fact, let me write it. Let me just fast forward. Okay, you have you have two. So you have the following thing. You have the gauginos. Let me call it. They are written like m1/2. They have a mass of the order of the so-called A terms. The A terms are some stuff generated here. They are interactions, okay, involving Higgs, 1 or 2, and the standard bosonic partners of ordinary matters. Okay, they have exactly the structure of Yukawa couplings. However, they involve purely bosons. Okay. And they have a coefficient here called A, okay? And A is of the order of the gaugino mass from this scaling, okay? This term here, it's very interesting, generates a mu term. This term here generates a mu term, okay? If you look at the auxiliary component of S, generates a mu term, and the mu term is of the same order as the gaugino masses. So the mu term it's very interesting. Okay, even if we start with mu equals 0, there you see that the presence of asymmetry over some protection mechanism sets the stage for the explanation of the size of the object. Okay, and in this case, if supersymmetry breaking takes place via non-renormalizable interactions, okay, then automatically you have mu generated by this term, and it comes out automatically of the order of the mass of the gauge genus. Okay, and this is of the order of m SUSY to the delta s plus 1 over m to the delta s. And then you have the scalar masses, the masses of all the scalar particles, including the Higgs, that is of order ms delta r plus 2 m delta r. Now notice that here now you have various options. Okay, you have various options. Now I don't know how to write. Let me write down here. You have various options depending on the dimensionality of delta s and delta r. Okay, the simplest situation is free field theory. Approximate free theory, where you have delta r is equal to 2 delta s of order 2, okay, equal to 2. Okay, in that case, all the masses are the same. m1/2 is equal m phi twiddle. So you get all masses of comparable order. Okay, all mass parameters are controlled by the same quantity. You can have the situation where delta r is larger than 2 delta s. Okay, you can have the situation here. In this situation, the scalar masses are suppressed. Okay, this is a situation where the scalar is suppressed, and if this relation is sufficiently strong, you have what is known as sequestering. Okay, that the information from this operator here is completely erased. And in some respect, this could be interesting because it is erasing part of operators that could induce flavor violations. Okay. However, the amount by which this can be obtained is again submitted to constraints from the bootstrap. Okay. And I don't know if you can find. I mean, you cannot go very far in this relation. I could draw another plot like the one I drew yesterday for the dimension of the Higgs versus H dagger. You can do something similar here. You don't have much space there, okay? But there is some space, but not much. And then there is another relation, okay? There's another possibility, and there's plenty of space, where delta r is less than 2 delta s, okay? Now, in this situation, the scalar masses are dominating, okay? So this is m1/2 bigger than m phi twiddle, and this other situation here is m1/2 much less than m twiddle phi. Okay. Now the situation here is known as approximate asymmetry. Okay, where the gauge genus are much lighter than everything else. This is not too good. Okay, this necessarily implies fine tuning, because the gauge genus, we haven't seen them. Okay, they should be at least of order 100 GeV. And if they're much lighter than everything else, including the scalar, the naive order magnitude of the scalar, this is all the scalar masses, then in order to explain why the Higgs has a mass of 100 GeV, we need to tune. Okay? So this case is not. So the two interesting cases are these ones. Okay? And in fact, the nicest case is perhaps the simplest, the one that everybody has worked in a naive way without thinking about deep conformal field theory, just dimensional dimension. It's just a simple thing. Now, the relation, however, the relation I wrote here are valid only at this scale here. Okay, and they are subject to RG evolution. Okay, these relations are subject to RG evolution, and RG evolution changes things in a dramatic way. Okay, changes things in a dramatic way. Basically, RG evolution tells you that this case here is not very much different than the first. Okay, the reason is the following: if gauge genus masses are much bigger than the scalar, by RG evolution, the gauge genus will affect the scalar, and they affect them in a very interesting way. They make the scalars more massive. Okay, so they stabilize them. In particular, that's what we want. We want the colored particle to have a positive mass, not to be tachyonic. So it gives a contribution to these scalars, and this contribution gets very quickly of sizable order. Namely, very quickly the scalars become of the order of the corresponding gauge genus. Okay, or not much less. That is particularly true in the case of colored guys. In the case of colored object, it takes about 4 decades of RG evolution to come in equilibrium. Okay, it goes very quickly. Okay, and similarly for all. So basically, you have a situation like that. Now, it should be said, like a technical thing, that in the early days of supersymmetry, people always started running the soft terms from this scale down. Okay. However, this without forgetting about everything here. However, this description makes it very clear that you have to start, that you have a certain class, you have a certain type of running in between here, and here you have another one. Okay. In particular, the scaling I was discussing here is already the running in this sector. That's relevant. So the ordinary running of soft terms that you find in all papers is the running that is purely determined by the supersymmetric standard model, is the one that takes place below the scale. Okay. Now I think I'm going very, very fast, and here I really cut through many things. So one thing is very important is that the class of terms that I have that I have derived in this way are what is normally known as soft supersymmetry breaking terms. Okay, in their first derivation, when they first appeared in the early 80s as a way to make supersymmetry breaking models realistic, let me say, what are the soft supersymmetry breaking terms? Soft supersymmetry breaking terms are just the following thing. Take a supersymmetric theory, and now add explicit breaking of supersymmetry, okay, via operators that are soft. In other words, that are of sufficiently low dimensionality not to spoil the good UV properties of supersymmetry, okay? And you can classify what these terms are. Basically, these terms are those and only those that do not reintroduce dependence on the UV cutoff, which in our case is the scale M. Okay. And there's a paper by Grisaro and Girardello that analyzes in detail. There's also in the paper of Georgiai and Dimopoulos on supersymmetry that is discussed, analyze in detail using spurionic technique and classifies these terms. Okay. Now I use a completely different logic, and I obtain the same terms. Why? Well, by my construction, okay. Since I've written the most general Lagrangian, by construction, I don't have any, given that the Lagrangian I've constructed is stable under quantum correction, given that it's the most general thing I can write down, okay, trivially, my conclusions are stable under any sort of quantum correction up to the high scale, okay. So in a sense, the soft terms are just a consequence of the presence of a robust construction, okay, where you write the most general terms. So in a sense, this is an alternative derivation of the soft terms. I don't know. This is probably more interesting for people who have worked on it than people who have never seen it, okay? But so soft terms are basically the most general thing you get when you just do dimensional analysis, okay? Now, how do I conclude this discussion? I have 10 minutes? 5-ish? 7, at least 7. So what I can discuss is the Higgs potential, okay? Electroweak symmetry breaking. So let me erase down here. Let me erase this. Oops. Yeah, this was far too much to put in one lecture. That's okay. So electroweak symmetry breaking. So to study electroweak symmetry breaking, you have to consider the Higgs potential. The Higgs potential consists, and let me just consider the Higgs potential along the relevant direction where you have 0, H2. This direction where the standard model is broken to U1. In fact, it's the only one you have to consider. You can prove in general that the vacuum is always going to be along this direction, if any, unless the symmetry is not broken. Okay, and the potential along this direction consists of the following thing. There's going to be some mass, h1 square. In fact, this is the absolute value, but let me just be very cavalier. There's this thing here, and there is M3. It's an off-diagonal H1, H2. It's an off-diagonal mass term. On top of that, you have the so-called D terms, G squared plus G prime square. These come from gauge interactions, H1 squared minus H2 squared. Okay, so that's the form of the Higgs potential. And now it's interesting, and it's very important to appreciate where we stand with supersymmetry. So the minimization of this potential, the origin of the weak scale that is spat out of this potential, gives us a relation between the weak scale and the supersymmetric masses. That is to say, the masses that were generated with that effect and which affects all the supersymmetric particles that tell us where these particles are. So there are two very quick things you can say about this potential. First of all, when is it stable? It is stable when this quantity, T, that is m1 squared plus m2 squared minus 2 m3 squared, is positive. If this quantity were negative, then you would go along the direction h1 equal h2, which is a flat direction, and the potential would be bounded from below. Okay, so this is the request for this is a classical discussion. Okay, what is the condition for supersymmetry breaking? Well, the condition for electroweak symmetry breaking, the condition is that the vacuum is unstable. That is to say that the mass matrix must have a negative eigenvalue. So the determinant of this mass matrix is negative. Okay. These are the two conditions. Now, this is the classical discussion. So what happens in reality is that these mass terms, are subject to renormalization. Okay, they depend on the scale. They evolve with the scale. Okay, and let me show you what happens. Okay, what happens is that you have the following situation. Okay, here I can plot either T or that M. Okay. In fact, let me plot here the lowest eigenvalue. Let me call M twiddle square H is the smallest eigenvalue of M square, okay, of the mass matrix. Okay. So the condition for electroweak symmetry breaking that this guy is negative and this guy is positive. And here I plot the RG scale, Q. Okay. Now, these parameters T and the mass of the light eigenvalue are very strongly affected by normalization, and the most important effects come from the top sector and the gluino. Okay. Most important effects come from the top sector and the gluino, and they are basically you have an effect of the following type. Okay, you basically have an effect of this type. Here it's dark. Let me write it here. You basically have an effect of this type. M2 twiddle square at a given normalization scale Q is given by the value it had at the original scale at the scale of matching supersymmetry breaking, minus an effect that goes like is proportional to 3 lambda top square over 8 pi square, the mass of the stops, okay, of the stop scalars, times a log of Q over ms over Q, minus a term that goes like, let me write it quickly, alpha top alpha strong over 4 pi squared m gluino square time log square, log ms over q square. And now, if you want the stop to be positive, okay, non-tachyonic, and the gluino is necessarily positive, the square of a fermion mass, what it happens is as you float to the infrared, okay, this is the first step in the solution of the G equation. When q becomes small, this logarithm becomes large. As you flow in the infrared, it's interesting that the lightest eigenvalue in the Higgs mass matrix becomes more negative. Okay, it goes towards being negative. So as you flow towards the infrared, if this eigenvalue had started positive, it goes. At a certain point, it crosses 0. Okay, it crosses 0 at a certain q critical, which it is roughly at the point. This thing here, q critical, is roughly at the point log of m over q critical, where alpha top over 4 pi is of order 1. Now it turns out 3 alpha top. Turns out that this is reached pretty quickly. So very quickly, this effect makes the Higgs mass change sign and becomes the term in the Higgs potential. So this is known as radiative electroweak symmetry break. In other words, the coupling, the presence of this very heavy fermi on the top, really induces in a way very much like Joe was saying before, like in Technicolor, would look beautiful. Okay, it seems beautiful. Okay, where's the problem? There's no problem. The problem is just nature. Okay, so now this thing crosses 0. This thing crosses 0, and then it keeps going. It keeps going. And where the scale is, well, if you started running at the Planck scale, this scale can be 10 to the 10 GeV. So it crosses 0, and you're still far from the toll booth. You go, and then it goes even more negative. So generically, when you stop running, that is roughly at the scale of the stop. Okay, when you go below the stop threshold, the stop stops contributing. Then you get. Generically, you get below the stop threshold, you get a contribution here that is equal to the original value, m2 square ms, minus something of order 1, m stop squared, minus something of order 1, m gluino squared. Okay? And now, the other thing you have to hope is that while you run here, t, this trace, never crosses 0. Okay, this thing should never cross 0. And in fact, it's easy to do it, but it's not always the case. Now, what is the deal? The deal is that now you have at the scale of the stop, when you integrate out the stop, you have an effective potential for the Higgs, okay, with a negative eigenvalue characterized by this relation. When you minimize this potential, you find the following thing. Okay, you find that the VEV, the expectation value V square, is roughly given by m twiddle. Let's call this the physical m2 twiddle. Physical. Let me write it better. M2 twiddle, m2 bar. Okay, m2 bar over g square. Okay, minus m2 bar. Okay, and that tells you that the VEV, the Fermi scale, is of the order divided by g times g squared is of the order of the stop. If you turn on this relation in the other way, what this implies, you see it right away, multiplied by g squared, it tells you that g square v square, that is roughly mz, is of the order of m stop, is of the order of m gluino. Okay? So the generic prediction of supersymmetry is not that the stop in the gluino is at 1 TeV, it's at 100 GeV. Okay? Supersymmetry where the mediation is at a sufficiently high scale that this logarithm, this alpha log, becomes of order 1. Okay? So the generic prediction is this, and this prediction is that supersymmetry should be discovered at LEP, not at the LHC. And we didn't discover it. So what is the deal here? Well, the deal is that what should happen, okay, if you still start from a very high scale, that for some reason your couplings, your masses are concocted in such a way that this goes, and it crosses zero close to the point where it's frozen. Okay? In such a way, the physical negative mass is only slightly negative. Then you have a separation between the weak scale and the scale of the stops and the other things that we haven't seen. But of course, you can see right away, the scale where this crosses zero has nothing to do with the soft masses themselves. It's just they are two unrelated parameters. The fact that this happens is an additional tuning. So the later we will see supersymmetry, the more supersymmetry will be tuned. Another option, and this is related to what Mariangela was saying the other day, is that for some reason, supersymmetry breaking takes place at very, very, very low scales, so that you don't run very much. Okay? So that this log is not large. If this log is of order 1, then there's still a loop factor between the Zima scale and the stops. Okay? But if this log is order 1, then the scale of breaking must be very, very low. Okay? That's a very special class of models. In that case, you get what Mariangela was saying the other day, the mass, given the mass of the Z and the mass of the Higgs, the mass of the stops and the mass of the gluino should be 500 GeV for the stops and 1 TeV for the gluino. And well, in the next 2 years, we'll see. Okay, thank you. Well, it was too much.